All right, so on this page here, we're going to talk about line symmetry. So draw in the lines of symmetry for each of the shapes. If none, leave the diagram blank. So line symmetry, you can think of this as a way that I could fold a shape or reflect a shape so that it matches right up onto itself, or we say carries onto itself. If I look at kind of this first star here, you notice that I could sort of fold it along, just right along this middle part. It would match up perfectly right onto itself, nothing sticking out. Or I could reflect it with a mirror and it would look the same this way. So here's a line of symmetry. Or I could fold it this way, or I could fold it this way, and it would still reflect right onto itself. Or here's a fourth line I could draw in. And there's one more. Here's a fifth line of symmetry. I could also draw that in. So here I have 5 lines of symmetry. And notice that I had 5 points, 1, 2, 3, 4, 5. I ended up with 5 lines of symmetry. On the second one, it kind of looks like you could draw a line here, just sort of by eyeballing this, but you might notice that this left piece is a little bit longer than the right piece here. So kind of a tricky problem here, just because it's a little misleading. So this actually does not have any lines of symmetry, even though it kind of looks like it could. For C, I have sort of a rectangle with rounded edges, and you notice right away I could fold it this way, hot dog style, or hamburger style, I mean. You could fold it that way, or I could also fold it hot dog style, just like that. It's not letting me put my line in a very good place, but you see what I mean. I could also fold it that way. So let me just go ahead and draw the line in. Sort of like that. So this has 2 lines of symmetry. For D, you could probably tell right away there's no way that I could fold this, not this way, not that way. There's no way that I could fold that and still have it match up onto itself. For E, I could fold this straight down the middle, just like a paper airplane. I could fold that straight down the middle, and that would match. For this letter Z, again, this has no lines of symmetry. It kind of looks like I could put one there, but that would not match up onto itself. I would end up with, a piece here or a piece there. So this would not work. Parallelogram is also kind of a tricky problem. Again, it looks like I could put a line here, but this would actually not work. I would end up with a corner kind of sticking out, just like that. So this would not work. Likewise, this would also not work if I fold it that way. So this actually has 0 lines of symmetry, even though it kind of looks like it has 2. But if you can't see how this wouldn't work, try cut out a parallelogram out of a piece of paper and see how to fold it. It's not going to work. For our last one, we have a regular hexagon, and you notice again I could fold this straight down the middle. That would work, or I could fold it this way, or a third way. This would also work. And a lot of people would just leave it at that. We'd see 3 lines of symmetry. They would leave it that way. But I could also fold these not only along the edges, but also along the vertices, along all these points sticking out. So I could fold it. Let me try to fix that. Let me make it a little straighter there. I could fold it this way, or I could fold it that way, or a 6-way here, just like that. So this has 6 lines of symmetry. And kind of the trick for this that you might notice, however many points there were, this had 1, 2, 3, 4, 5 kind of points sticking out. This had 5 lines of symmetry. Or here I had 1, 2, 3, 4, 5, 6. This had 6 lines of symmetry. That's kind of the trick to sort of check yourself on that. Let's look at the next part. This says determine the order and the angle of rotational symmetry for the following shapes. So order just means how many ways could I turn this and still have it look the same? So it's still kind of talking about symmetry, but sort of how many different ways can I turn the star and it still looks the same? So here I could turn it this way, 1, 2, 3, 4, 5 different ways, and it still looks like a star. I wish this would match up a little better, but this is 5 different ways that I could turn that. So my order is 5. To get your angle is like how far did I turn it from here to here? How many degrees did I turn it to make it match onto itself? And the easiest way to do this, 360 degrees is a full turn, and the order was 5. So I'm just going to divide 360 divided by 5, and I get 72 degrees. All right. For my next one here, what's the order of this weird upside down L shape? I can't really turn it any way. None of these ways are going to work. So this has an order of 1. There's only one way that it could be turned. And so 360 divided by 1 is just 360. So this really has no rotational symmetry. If it's 360, that's not really anything. For this shape, so again, how many ways could I turn this? So here's one way, or I could turn it upside down, 2 ways, and then just back to the beginning. So this has order of 2. All right, and to get the angle, how far did I rotate that? I'm just going to do 360 degrees divided by the order, 2. So if I divide this by 2, my angle is 180. There you go. And then for this last shape, here I didn't make a shape, but here there's no way that you could turn this and still have it match onto itself. So just like with this shape, my order would be 1. The angle would be 360 divided by 1 is 360. So this really has no rotational symmetry, even though it kind of looks like it does. And let's look at that last part here. Determine the following symmetry characteristics for these polygons. So how many ways could I turn this and still have it look the same? The triangle, this would have an order of 3. There's 3 different ways that I could turn this, and it would still look like that triangle. What about the lines of symmetry? So how many lines could I draw in here? You see I have a line here, a line here, and a third line through this point. So this has 3 lines of symmetry and a rotational order of 3. For the square, I'm just kind of doing the same thing here. I could turn it this way 90 degrees, that way 90 degrees, this way 90 degrees, or I could turn it that way 90 degrees. So this has a rotational order of 4. And if I think about how many ways I could fold this, I could fold it kind of along this line in half or along this line in half. I could also fold it diagonally this way or a 4th way like this. So you might start noticing the pattern here. I had a rotational order of 4, lines of symmetry 4. So you might be able to see the pattern here for regular polygons. Let's look at another one. Here I have a pentagon. I could fold it 1 way, 2 ways, 3 ways, 4th way, or through this corner here a 5th way. So this has 5 lines of symmetry. And have you guessed what the order would be? There's 5 different ways that I could turn this. Or again, the shortcut, just kind of count all these points. You have 1, 2, 3, 4, 5 points. That's kind of the shortcut to sort of count how many corners you have there. All right, so you might be able to guess the last one before I do the last one. But the hexagon, we already did this. So this had 1, 2, 3, 4, 5, and then 6. We already did this one. This had 6 lines of symmetry. All right, and the rotational order, yeah, you probably already guessed it has to be the same. This would have 6 different ways you could turn it. So again, that's kind of the trick for regular polygons. Whatever your lines of symmetry are, that's going to be your rotational order. Or you could just count, really, you could just count your points. 1, 2, 3, kind of 3 corners sticking out. We'll give you 3 lines of symmetry, 3 rotational order. That's your trick here. All right, so hopefully this one should be a little bit easier for you. Again, just if you're doing the notes, make sure you're filling the notes along with the video.